Good afternoon. This is Group 1. My name is Liza, and we'll be presenting our research paper presentation today with my teammates, Saranya, Matthew, and Sal. So the paper we're going to be presenting today is Occupy the Cloud Distributed Computing for the 99%. It was published in September 24th, 2017 in a conference of proceedings of the 2017 Symposium on Cloud Computing. So to start it off, we're going to go over a quick definition of what distributed computing is, since that's what the paper is talking about. And distributed computing basically is defined as a system of multiple computers or nodes with multiple software components. And they basically run as a single system with the aim of solving one complex problem. And it usually uses parallel processing to achieve that aim. And we can see distributed computing quite often in cloud computing, especially in platforms such as AWS, Salesforce, and Dropbox. So the problem that the paper addresses is that while distributed computing is very popular nowadays and is provided by so many platforms, there are still few users that use these services. And this is due to two reasons. The first one being the setup complexity that's associated with the distributed computing platforms, and as well as the management and cost overhead. So by setup complexity, this is basically the decisions that are related to the cluster computing setup, as the user needs to make so many decisions when they're setting up their cluster online, such as instance type, cluster size, pricing model, programming model, and task granularity. And in addition to that, the cost is very high. It's expensive to set up a cluster computing, and the management responsibility basically falls on the user themselves. So that being said, this formed the motivation of the research, along with the complex planning and workload management that's associated with cluster computing on the cloud. There's also like complex applications and programming frameworks that are not easy for neither the typical user to understand or the more advanced tech user. And it also includes complex layers of abstractions that are difficult to configure. So to that end, three objectives are defined within this paperwork. The first one obviously being that they wanted to provide a simpler and easier setup for these distributed cloud computing services. In relation to that as well, the users should be allowed or provided the option to run their existing code on their devices on whatever node that they're already running, and kind of migrate it and run it on the cloud service. And that should be provided as an option to make it like easier to migrate to the distributed cloud computing platform. And lastly, the last objective was to allow the users to be able to run multiple jobs and a bigger number of jobs at the same time with better performance. This is achieved. Next slide. So this is going to be achieved through a few methodologies. We're going to go into details in them later on through the presentation, but to kind of go over the main ones. So a serverless execution model was implemented in this project, and using stateless functions. And by stateless functions, we mean that the functions will be executed in a remote container where it's deployed, and its state is going to be stored in a remote storage device. Every time the remote device receives a new input, the function is going to be invoked again. And the two other methods that were used that are related to either computer-bound workload, where function-level parallelism was employed, and relating to data-bound workloads, simpler versions of the MapReduce framework were applied. And lastly, simpler abstraction was used, where users don't need to set up or configure servers for arbitrary functions. And next up, the technical analysis will be presented by Saranya.
Yeah, hi everyone, I'm Saranya. Thanks, Liza, for introducing the topic and discussing the problem statement. The next part is the technical aspects of the paper. I'll walk you through that. Yeah, before getting into the modest proposal, the authors have discussed some of the problems that exist with the server-oriented architecture. They are usage of multiple resources like CPU, memory, and the network bandwidth. And the other one is the server maintenance. Due to its long running nature, we need DevOps support for maintaining the server. In order to overcome these problems, the authors have proposed the idea of using serverless architecture with stateless function. As Lisa explained, in the serverless model, the function is deployed only once and it can be invoked repeatedly whenever new inputs comes in. And this model, it elastically scales up with the input size. And also the stateless functions, it helps in simplifying the programming and also the deployment for end users. Even though other researchers have used the serverless model for implementing the data processing systems, in this paper, authors have used a simple API that is tightly integrated with the existing libraries. So that is the new idea proposed. And also the authors have tested this implemented model with different workloads to study the performance trade-off of this approach. Next is the system architecture or the system components. So the main components required for executing the stateless functions are a fast scheduler, is a global scheduler is required, and also the overhead execution time should be low, and the remote high performance remote storage is required. Here you can see the system architecture with the global scheduler and the container is created. So let's see how this function works. User will, first of all, user will submit a single threaded function, that is the execution of instructions will be in a single sequence. So that is the single threaded function. It is passed to a global scheduler. Once the scheduler determines whether a function is supposed to run, an appropriate container is created for the duration of the execution. And also here user will have a control to interpret the runtime dependencies whenever required. That is the advantage in this. Next, let's go through some of the features of the system. They are simplicity and fault tolerance. As I have mentioned earlier, to talk about the simplicity, the prototype developed, it has a minimum infrastructure with a simple API. It does not include any complex functions, data flows, or any distributed data structures. And other one is the fault tolerance. Whenever a failure occurs, then in that case it will be restarted at a different location, and also it can execute on the same input. Wherever it is stopped, it will execute from that point. And the succeeded functions can also be tracked using the atomic writes. Next is the comparison of the related models. The authors have compared this. They have used different storage medium and the write speed is compared. Some of the similar systems like Lynda, Celius, and database trigger systems, they are mainly used in shared file systems. And one disadvantage is that they don't follow any specific programming model. And also the prior work shown there is no significant performance benefit or any performance improvement when we use the hard disk locality. And to check the performance, a comparison is made with input output throughput of storing the data on local SSD of Amazon EC2 instance versus storing the data on S3. So here the table shows the comparison. So this shows that writing to a remote storage is faster than a single SSD. So this is only with the single SSD. But when we use multiple SSDs, then it can yield a better performance. So that is what the result observed. And then let's discuss the PyWren prototype. To evaluate all the previously discussed ideas, the PyWren 2 is developed. It seamlessly exposes a map primitive from Python and top of AWS Lambda. So, though this Lambda function was specifically designed to run event-driven microservices with a fixed function, here in this case, during runtime, it is invoked with different functions. This is done by extracting the new code from S3. And next comes the PyWren and AWS Lambda specifications. Here, the PyWren, it serializes a Python function using Cloud Pickle. So this Cloud Pickle is especially used for cluster computing. It captures all the relevant information and eliminates the majority of user overheads, such as deployment, packaging, and code versioning. So this is an advantage of this. And the runtime, if you see, it takes maximum of 300 seconds of execution time, and the RAM is 1.5 gigabytes, and the storage is 512 megabytes, and it is stored locally. Next is the working model. Yeah, so this PyWren submits the serialized function along with the serialized datum. So this is done by placing them globally unique keys in S3, and a common Lambda function is invoked. So when you see on the server side, this PyWren invokes the relevant function with the relevant datum. So both are extracted from S3. And finally, the result of the function invocated is it is serialized, and then it is again placed back into S3 at a pre-specified key. So the job completion, it is indicated by the existence of the key. This is how it works. And also in this way, PyWren, it is able to reuse the registered Lambda function to execute different user Python functions, and it mitigates the high latency for function registration. So that is other advantage of this. So next is PyWren map for everyone. So this map primitive, it addresses the problems with respect to the remote invocations. When a map function is called, it launches as many as stateless functions, and as there are elements in the list, that is how it works. And another key aspect is that this API, it mirrors the existing Python API for parallel processing, and also it integrates easily with the existing libraries. So this helps for data processing and data visualization, etc. And next is about the benchmarks to determine the impact of using the remote storage for input output and how this scales with the workers count. So, and the performance trade-off with different workload is visualized. You could see the graphical representation here. In terms of compute, a matrix multiply kernel is ran with the Lambda, and the result observed is it is found that like 18 giga floating points per second per core is observed, and it scales to more than 40 tera floating points per second while we use 2,800 workers. And to measure the remote input output throughput, read and write bandwidth, that is benchmarked to S3, you can see in the second graph. As a result of this, on an average, if you see 30 megabytes per second write and 40 megabytes per second for read per lambda is obtained. And also this scales to more than 60 gigabytes and 80 gigabytes of read when we increase the workload. Next is the applications of where PyWren is used. Some of the applications that use PyWren are computational imaging, scientific instrument design, solar physics, and object recognition. Another interesting area where PyWren is used is at NASA's Solar Dynamics Observatory, where they use for extracting some solar imaging data for some solar flare prediction. And also it is used in the three-dimensional super resolution microscopy to design some new novel types of microscope functions. So these are the applications. And next part will be explained by Sal.
All right, Saranya, thank you very much. Now, the next part we're going to analyze about the paper was how the authors of the paper applied various abstractions to PyWren to incorporate it into a lot of industry standard applications and use cases. So the first abstraction we're going to talk about is what's called a map and monolithic reduce. So the goal of this abstraction is, as a task with multiple functions is executed, the results from those functions, which are map operations, is obtained and stored on one machine that will be used to process that data. The methodology to execute this is like the gather library in high performance computing. So this task is what the goal of this abstraction is. The use cases that the authors cover are mainly related to the formation of a machine learning model. So how do you form a machine learning model? That consists of two components, the process of featurization and actually building the ML model. So PyWren is doing both of those things in this abstraction. So in terms of featurization, when gathering input from data, a large set of data, the task executes stateless functions to analyze the large data set and categorize it into small sets of categories, or also known as features, for the machine learning algorithm to create a model. These categories are called features. For the learning portion of the functions, the machine learning algorithms are used to analyze the features and perhaps weigh them to compile and create a model. So how does this application sequence run? So first of all, it initiates a map sequence and runs the sequence using stateless functions to gather the features. Then we see the learning stage follows that. And the important distinction here is that when you're running something on a large set of data, typically you require a distributed computing cluster to make it run efficiently. But the whole goal with PyWren and what the researchers and authors found was that they could make a large operation, building this large model, run pretty well on a single high-performance computer as long as they had and successfully implemented efficient multi-core libraries. Now moving on to an example use case of machine learning image analysis. So the researchers performed an analysis on 1.28 million images from a publicly known library called the ImageNet Large Scale Visual Recognition Challenge. And what happened with this was the code and the libraries that they used were already predefined. They consisted of GIST descriptors for web scale image searching and other analyses. In this experiment, the technology they used was AWS Lambda, as we saw explained earlier by Saranya. They used 3,000 Lambda workers. They analyzed feature data. They gathered it, transmitted it from Lambda to and stored the data on S3. The total time taken to do all of this using PyWren was 113 seconds. So what did we see in the machine learning image analysis findings? The monolithic MapReduce operation is run on the instance in question. The time taken to obtain features from the S3 instance only took 22 seconds. And the time taken to build the machine learning linear classifiers took 4.3 seconds. So really what they found was, one, Elastic Compute 2 AWS instance was capable of performing ML featurization of a pretty significant large set size of data. So the second abstraction we have here is using MapReduce. The goal of this abstraction was to implement the BSP model. BSP model stands for Bulk Synchronous Parallel Model. So the whole concept of BSP was explained by Rutgers University in another research article we found. So BSP contains a computational task, essentially. And this computational task is divided into subtasks. Each task is what we're going to call super step. So each super step contains a set of compute processes, and each of them consists of the same code running in parallel. The super step ends once all the computing tasks end. Now, we also have a barrier, and the barriers in the BSP model are meant to act as a synchronizer. So once each task completes, the generated messages in the model are sent to the next super step. The barrier synchronization responsibility is to make sure all the task generated messages are sent to the next step. The next super step starts only after all input has been received and received from the previous super step. And this process continues in a loop style fashion until all processes vote to halt and all messages are sent and processed. In this abstraction, high bandwidth storage in AWS allows for process shuffling across superstep stages to easily take place when using this MapReduce abstraction with PyWren. Going further in this abstraction, they also implemented PyWren as a word count program. So the technology, we're also using AWS S3 to store process shuffle data and PyWren for the API to gather this word count. So the data that they used for the word count was 83.86 million Amazon product reviews. And they partitioned these product reviews across 333 software data partitions. And using PyWren to count the words using PyWren and S3 to store the data and execute the stateless functions and processes, the total time of execution that this task took was 98.6 seconds. Now, they also contrasted this for comparing to using a PySpark library with 85 R3X large AWS instances. And the specs of these, each machine had 4 cores to match the PyWren specifications. The total execution time of this was 84 seconds. So as you can clearly see by these different findings, the difference was only a 17% difference. And the important thing is this difference does not include the intensive labor that it takes to set up a complex clustered 85 cluster computing environment using PySpark with AWS. So the reasons for the slowdowns that the authors came up with were, number one, the latency that stemmed from the S3 writing and reading, and also that the PyWren library does not natively support parallel shuffle block reads. The researchers also explored PyWren and shuffle-intensive workloads. So using 1 terabyte of data, they performed the Daytona sort benchmark to measure exactly how PyWren can perform when the task payload contains many shuffle-intensive operations. So in this experiment, they implemented the TerraSort algorithm in 2 different stages. The partition stage, it divides the data input in a range, and then after the data has been partitioned and stored, performs a write of the output. In the merge stage, it loops through each partition and sorts and merges all the data that is considered intermediate for the given partition, and then it again performs a write of the output. The total files that are shuffled, they shuffled were 6.25 million sorted files, intermediate files. And then you can also see the performance breakdown as well for the terabyte of data as well on in this figure. Now we're going to go on to the observations of this experiment. So the authors observed that when the levels of parallelism are increased, so is the overall job performance. However, the increase is inhibited by the throughput bottleneck of the Redis shards that are used for intermediate storage of data due to S3 limitations in regard to the high request rate of small objects that this experiment is using. So we see that there are some limitations in parallelism and job performance. So the researchers also noticed that when the number of workers was doubled from 500 to 1,000 Lambda workers, there was a 42% increase in performance. And as the number of Redis shards increases, so does the performance. So those two metrics are directly correlated with performance. So now we're going to look at resource and allocation costs in terms of Lambda workers and Redis shards. So as you can see in this cost figure, the cost remains at a mostly stable baseline according to the authors, even though the number of Lambda workers was increased to further bolster parallelism performance. So you can see that even though as Lambda workers are increased from 500 to 100 to 500 to 1,000, the cost remained at a fairly stable baseline here. So rising costs do not necessarily correlate with adding resources to the environment in terms of Lambda workers. Final abstraction, which the authors didn't spend too much time on, but that we wanted to mention and analyze, was using PyWren in terms of a parameter server. So the researchers used PyWren to implement applications that behave like a parameter server. And a parameter server, in a very brief definition, is an application that distributes computational task workloads from the server node to client nodes using the server node to dole out and refer to global parameters to. And these parameters are shared among all the client nodes for data processing. So the researchers discussed the possibility of using PyWren in a stochastic gradient descent application, such as HogWild. And also the researchers noted that these types of parameter server applications, which calculate gradients like this HogWild library of functions, work well with the stateless function model of PyWren, because the one parameter server is responsible for coordinating task executions across state functions using those globally shared parameters. Okay, and now I'm going to pass it off to Matt for our discussion.
Thank you, Sal. In this section, the authors discuss the performance, limitations, and challenges of existing infrastructure and compare it to their proposed PyWren. The main issues covered in this section include resource balance, pricing, scalable scheduling, debugging, distributed storage, and launch overheads. Resource balancing. What is it? Resource balancing deals with how a function resource usage is allocated. The current limits of resource balancing in serverless design are extremely low. While the authors don't specify how PyWren addresses this issue, they do discuss how existing infrastructure could begin to develop a solution. Functions are stateless, and they need to transfer both input and output over the network. As memory capacity and network bandwidths grow in the incoming years, these rules could potentially derive memory capacity from a target running time. The authors talk about Amazon Web Services as an example. AWS Lambda has a 35 MB per second bandwidth to the storage object, or S3. S3 has a memory of about 1.5 gigabytes and can thusly be filled up in about 40 seconds. Assume it takes another 40 seconds to write output. So keeping all these in mind, we can derive about 80 seconds of input and output and around 220 seconds of computation from a given 300 seconds of running time. Pricing. Current cloud providers force users to pay a premium for elastic computing. With advantages including simplicity, substantially finer-grained billing, and higher resource utilization, this premium may seem worthwhile to some. However, pricing for on-demand or hourly instances of AWS Lambda can vary greatly and can be harder to understand. So as a solution, the authors draw attention to PyWren's disaggregated architecture. A benefit of this type of architecture is much simpler cost estimation and prediction. In the near future, the authors hope to develop a way to automatically predict the cost of computations using PyWren. Scalable scheduling. The main issue of scalable scheduling in existing architecture is finding a way to provide low latency scheduling for data parallel frameworks running on servers. In order to implement low latency scheduling, certain information regarding the cluster status is necessary, including but not limited to which containers are free, resource heterogeneity, and input locations. In most, if not all, of the current infrastructure, this information is only visible or available to the infrastructure provider, whereas the users only have access to job structure or how functions depend on each other. The authors plan to first determine exactly what information needs to be exposed to users by cloud providers, and after that, they plan to research scheduling techniques that can handle the separation and exposure of cluster status information in the hopes of implementing it into future models of PyWren. Debugging. So where's the issue? The challenge of debugging in PyWren results from difficulty facilitating the communication and cooperation between system components. PyWren is composed of multiple system components. For example, PyWren uses CloudWatch, a tool provided by Amazon Web Services for monitoring Lambda execution. To understand how a job was carried out would require the aligning of events from both Lambda and the host. The authors explained the issue of debugging in PyWren, however, offered no real improvements or solution. Distributed storage. PyWren separates storage and computing in their programming model. Performance challenges can result from this separation, some of which include unreliable support for large, shuffle-intensive workloads, and not lacking API support for append systems like S3. These various performance challenges brought about a call for more efficient distributed storage systems. In the future, the authors plan to address these challenges by enabling a flat data center storage system and developing a common API for storage backbends capable of powering serverless computation. Launch overheads. Function invocation is one of the main challenges in PyWren. As a combined result of Lambda invocation rate limits imposed by Amazon Web Services and the time taken to set up PyWren's custom Python runtime, function invocation can take anywhere up to 20 to 30 seconds without any sort of caching. As possible ways to address this issue, the authors plan to research if the same techniques used to make VM forks cheaper can be used to improve latency. Some of these techniques including layering file systems or caching containers. They also plan to determine whether the scheduler can be modified to queue functions before their inputs are ready to handle launch overheads.
All right, Matt, thank you very much. Now we're going to just briefly review our own analysis of the PyWren library. And we're going to first feature some of what we consider pros of the PyWren library and API. And we're also going to list a set of proposed improvements we think could be made to PyWren. So the first pro of PyWren is really allowing the use of the cloud for research and really any activity to be more accessible to anyone that needs it. So the authors created a publicly accessible library that makes the execution of research and commercial activities on the cloud more accessible. And this is really done by negating the need for complex computing clusters to perform high intensity computing tasks, as we saw things like machine learning model building. The second pro of PyWren is in relation to the serverless architecture that we see and also the stateless functions. So the researchers implemented a serverless architecture where a stateless function is deployed once and invoked repeatedly whenever new inputs have arrived. This is instead of deploying a conventional server-oriented model, which really is more complicated and more costly to implement. We also see the cost and additional compute power don't necessarily equate to each other, and the two aren't correlated in all circumstances. So we saw that while using the PyWren library, the researchers showed that as they add more Lambda workers to increase parallelism, that the cost of the resource additions did not drastically increase and remained at a stable baseline, which supports the goal of furthering making cloud computing more accessible. The final pro we see is PyWren is used in a diverse set of applications. So the researchers really demonstrated very well that PyWren is being applied to many areas of research and industry and really proving its performance and its worth. This can be anywhere from, we saw computational imaging, we also saw scientific instrument design, we saw it being used in NASA with solar physics and object recognition as well. All right, moving on to some proposed improvements we see with PyWren. So starting off with the BSP framework implementation, it's unclear exactly how they implemented the BSP framework into PyWren or its applications, and the performance benchmarks were also not very clear with how it was integrated. The second improvement we saw could be made was in terms of the parameter server performance. So PyWren's performance should be measured when it's deployed into a parameter server application using Redis and memory key value stores to verify that it can actually produce not only acceptable results, but also desirable results. And the final point we wanted to note was making this technology accessible to other cloud platforms. So throughout this entire paper, and including even the title, the author's goal of making cloud computing accessible for the 99% was not fully fulfilled with PyWren, because it should really include, if you want to make it completely accessible to everybody, enough modularity and extensibility protocols to be compatible with and run on other cloud providers, because AWS, while it's the largest cloud player, may not be available in all regions. So these other cloud providers can include the Google Cloud Platform, Microsoft Azure, and other technologies as well, like the Tencent Cloud and things like that. Okay, and this concludes our presentation on the PyWren library and our research paper. We thank you very much for watching, and if you have any questions, you can leave them down in the comments below. Thank you very much, and have a great day.